Hello there, and welcome to the Checkback Testing Theory training video. This video covers the basic theory of why we need checkback, what checkback is, how does checkback work, and how to interpret checkback alarms. This training will cover the checkback testing features supported by TC10B, UCBS, UPLC, and UPLC-II. To understand why checkback testing is needed, we should first review the types of radio frequency modulation power line carrier systems utilize to send information over the power line. There are two major modulation types used by power line carrier: amplitude shift keying (ASK) and frequency shift keying (FSK). FSK is used on schemes such as permissive overreaching transfer trip, directional comparison unblocking, and direct transfer trip. FSK in the idle state always transmits guard, typically at a lower power level to the other end of the line. This allows the receiving end to continuously know the current state of the communication path on the power line, as well as provide an early warning if the signal level starts to degrade. In this diagram, the calibrated received guard level is shown in green. If this signal degrades for some reason, then the fade alarm will be triggered when it reaches the program fade alarm threshold. This threshold is set at a receiver level that still allows for the protection scheme to operate. If the signal continues to degrade, then the received signal will eventually be undetectable by the receiver. Once it drops below the fade margin threshold, the protection scheme will no longer operate. When it reaches this level, the system loses the good channel output. Amplitude shift keying (ASK), or more commonly known as on-off or carrier, is used solely on directional or non-directional comparison blocking schemes. An on-off system only transmits when sending blocking. This diagram shows a received blocking signal in green. 99% of the time, the on-off carrier channel is off, and there is no indication if a blocking signal will get through based on the current conditions. Checkback testing provides a means to determine if the communication path on the power line is still working and sends a checkback major alarm if the blocking signal cannot be sent or received. The blocking signal normally transmits at high power, 40 dBm, 10 watts typically. Enabling low-level testing allows for additional checkback testing at typically 30 dBm or 1 watt. This provides an early warning checkback minor alarm that indicates that the signal level is degrading before the blocking signal is lost completely. What is checkback testing? Checkback testing is an optional feature supported in our older TC10B and UPLC, as well as our current UPLC-II carrier products. AMETEK also offers a universal checkback standalone product that can be connected to non-AMETEK carrier products to make them checkback testing compatible. The catalog number will reflect if your AMETEK powerline carrier equipment has the checkback option. For the TC10B, it is the 3rd position, and for the UPLC, it is the 8th position. An A indicates that this unit was shipped with checkback testing, and an N indicates it did not. There could be a chance that checkback was added after shipping, so you should physically verify if the checkback module is installed for the TC10B and that the electronic catalog number of the UPLC shows an A. As a reminder, for the rest of this training I will say UPLC, but this applies to any of these products unless noted. Checkback allows for periodic testing of the communication path via the transmission line so that if there is a degradation of signal, then a checkback major or minor alarm will be asserted. If the low-level test cannot be received, but the high-level test signal can be received, then the communication path is degrading, but there's still enough margin left to receive blocking. In this case, checkback minor alarm will be asserted, which is similar to the FSK fade alarm. If the high-level test cannot be received, then a checkback major alarm is asserted. This is similar to the FSK good channel output, as it indicates that the signal strength is too low for a blocking signal to be received and the protection scheme may no longer operate. If both checkback major and minor alarms are set, this indicates that the UPLC is not receiving its own checkback testing transmissions. Checkback testing can either be internally initiated by the UPLC automatically or externally by the relay or other means. How does checkback testing work? The UPLC at each substation is assigned a checkback address. For an end-to-end line, one substation would be designated master and the other substation remote 1. For a 3-terminal line, the 3rd substation would be remote 2. UPLC allows up to 10 remotes, but in the real world, a 4-terminal line would be the maximum recommended due to line losses and tuning issues. For this example, we would stay with a 3-terminal line, which also covers the 2-terminal end-to-end line scheme. There are two methods for addressing the individual UPLC, coded or timed. When using the timed mode, low-level blocking and high-level blocking signals are keyed for a single pulse of specific duration. Once a time mode checkback is initiated, the master will send a checkback test signal to remote 1, and remote 1 will respond. If there is a remote 2, then the master will send a test signal addressed to remote 2, and remote 2 will respond. If low-level testing is enabled, then a test will be sent twice for each UPLC. Once at low-level RF, 1 watt typically, and then once at high-level RF, 10 watts typically. The duration of these pulses indicate the checkback address. A 5-second pulse is master, 10-second pulse is remote 1, a 15-second pulse is remote 2, etc. The master initiates a checkback by sending a 10-second pulse. If remote 1 receives a 10-second pulse, then it transmits a 10-second pulse in response. Again, if low-level testing is enabled, this is done first at low-level RF and then repeated at high-level RF. For a 3-terminal line, the master will repeat all this using a 15-second pulse that remote 2 will respond to. When a remote UPLC initiates checkback, the testing cycle looks like this. The initiating remote sends a 5-second pulse to the master, which responds with a 5-second pulse, and then corresponding pulses to the remaining remotes. Time mode checkback tends to be less susceptible to noise due to just being a single pulse of a specific duration, but takes longer to complete. It also has the limitation that only the initiating UPLC will generate and clear alarms. This is typically the master UPLC, as it should initiate checkback testing first if the clocks of all the UPLC are synchronized. When using timed mode, if you need the responding ends to also generate and clear alarms, then checkback needs to be initiated separately for each UPLC at a different unique time for each UPLC on the line. When using auto test in hours of the day, there are 4 distinct hours of the day that can be programmed for checkback testing. Typically, at least one of the test times is set the same for all the UPLC. Here's an example for a 3-terminal DCB line. First, the checkback settings for the master are set for 0300, and the second master checkback is set for 1500, 12 hours later. Since these are the only 2 times I want the master UPLC to initiate a checkback, I will set the remaining times to all 0300, as duplicate times are ignored. Remote 1 I will also set for 0300 and 1500, and remote 2 I will set for 0300 and 1500. I do this so that if the master fails to initiate a checkback at these times, then the next remote will initiate. Then remote 1 should have at least one unique test time so that it can set and clear checkback alarms. So I set 0400 1 hour after the master checkback, and again at 1600 hours. Remote 2 should also have its own unique test time, so I will set that for 0500 and 1700, 2 hours after the master and 1 hour after remote 1. When using coded mode, the checkback test will use the blocking signal as a 60 bits per second data stream to communicate between units. Because the type of test, low or high power, and checkback addresses, master, remote 1, etc., are included in this data, both the master and remotes will set and clear alarms. Additionally, since we do not need the extra checkback test for the remotes, the state of the communication path can be determined quicker, instead of waiting the extra hour or 2 hours. The coded mode sequence looks like this. The master sends a request to remote 1 responds and sends a request back to the master. The master responds back to remote 1, and then remote 1 acknowledges. If low-level tests were enabled, the first sequence would be at low-level power and then repeated at high level. If more than one remote is in the system, the sequence will repeat for each of them. You can review the sequence of events for all of our products to determine what is going on with checkback testing. The UPLC and UPLC-II records not only checkback, but all events, unlike the TC10B and UCBS, which only record checkback events. Here are UPLC-II SOEs from a remote 2 of a 3-terminal line. At 0:3200 hours, there is a master clock sync. Then at 7:10 and 18 seconds, a low-power checkback test from remote 1, followed by remote 2 showing a pass test at 7:10:22. Then at 7:10:26, a high-power checkback test from remote 1, followed by remote 2 showing a pass test at 7:10:29. Notice that the received power is 10 dB higher for the high-power test versus low-power test. Then 11:05:10, a high-power checkback test from the master, followed by remote 2 showing a pass test at 11:05:14. As you can see, coded mode is much quicker to run than time mode. both in the actual test duration, as a Remote 1 to Remote 2 test only took a total of 11.5 seconds for both low and high level testing in both directions. If doing this in time mode, it would be at least 1 hour to get this same information. In time mode, you need to wait for all ends of the line to initiate a test to get the current state of all ends of the line. From the 3-terminal time mode test schedule example previously shown, this would be at least 2 hours. However, coded mode does have its drawbacks. Coded mode is slightly more susceptible to noise due to it being a data stream, so that data can be corrupted during thunderstorms or other noisy events. Also, because it uses the blocking signal as a 60 bits per second data stream, it tends to fill up external recording devices. There is a programmable output to indicate that a checkback test is being executed, but that needs to be designed into the station design and requires a recording device that has an input for disabling event recording while active. Also be aware there's a small delay for the receiving ends to assert the output, as they first need to determine if this is checkback. So at the remote ends, there will always be a burst of data recorded before the output is asserted. This state table for checkback testing provides the most likely failures depending on the checkback major and minor alarms at the master and 1 or more remote stations. Using this information plus the sequence of events log from each of the UPLC should provide a good picture of what is going on with the system. You can utilize the table immediately after a full checkback test has been completed from at least one end for coded mode, but you would need to wait until all the remotes have had a chance to initiate checkback for time mode, as they would need to set their respective checkback alarms as well. To read this table, you would take the checkback test results from the master and each remote one at a time and determine the most likely location and/or cause. If only the low-level checkback fails, then the checkback minor alarm will be generated. If the high-level checkback fails, then only the checkback major alarm will be generated. If the initiating end does not receive its own checkback test, then both the major and minor alarm will be set. For example, if both the master and remote have a checkback major alarm, then that would indicate the line has failed. If the master has a checkback major alarm and the remote had both a checkback major and minor alarm, that would indicate that the remote has failed. If the master and remote both have checkback minor alarms, that would indicate a weak or noisy line, as only low power tests have failed, not the high power. So in summary, checkback testing provides a method to automatically and periodically test the transmission line RF path between direct comparison blocking power line carrier devices. It may be implemented to provide not only complete loss of communication failure alarms, checkback major, but early warning degrading communication alarms, checkback minor. Sequence of event logs and the alarm states at all ends of the protection scheme provide a useful analysis tool for both determining the current state of the line and determining causes of misoperations. In the next video, Checkback Testing Advanced Theory, we will cover in more detail the various checkback setting features and how they affect operation. That is it for this training session. I hope you found this session informative. If you have any questions regarding Powerline Carrier, please contact us at the following phone numbers or emails. The sales email may be used to contact AMETEK for quotes or ordering new equipment. The repair email may be used to contact AMETEK for repair of existing equipment, and the applications email may be used to contact AMETEK concerning product setup or Powerline Carrier system applications. Also, please make sure you can receive emails from pi.marketing@ametek.com if you want to receive the latest news concerning AMETEK Powerline Carrier products, product advisory letters, and conferences. You may also go to our website for further Powerline Carrier products information such as PDFs of product manuals, product advisory letters, and firmware downloads.